the LHC second chapter of LHC event here on high energy physics. Our speaker today is Tao Han from University of Pittsburgh. Tao Han received his PhD at the University of Wisconsin at Madison. After that, he was a postdoc at Fermilab, and after his postdoc, he moved as a professor to University of California at Davis, where he was from 1990 until 1997. In 1997, he moved to his PhD University of Wisconsin, where he was a professor until 2011. And since 2011, he's at the University of Pittsburgh. He is currently the director of particle physics, astronomy, astrophysics, and cosmology center at the University of Pittsburgh. He's a member of many advisory boards at different places, and a member of editorial board of several magazines, several journals. He is also a recipient of many prestigious awards in the US and in China. His main area of research is particle physics, high energy physics, and of course, as we know, the most recent events in the most big event in particle physics is discovery of Higgs. So today, as we expect, Professor Tao will tell us about the interpretations, expectations, and perspectives in particle physics. Thank you.
Thank you very much. Thank you, Dimitri, for such a nice introduction. And it has been a great pleasure to be here. It's not only for this very stimulating environment for research and for our workshop, but also for the beautiful surroundings. That certainly has made my colleagues in North America very jealous for me to be here. So today, I'm going to discuss the recent excitement and looking forward to see what we may push for and what may be expecting for new physics. So I want to discuss this, the Higgs discovery, and also what may be the new physics associated with the Higgs, what we want to answer deeper questions in connection with this particle physics. As Dimitri said, now I'm from the University of Pittsburgh, and Pittsburgh is a very nice city. So this is the picture of the downtown Pittsburgh area. There are similarities with Natal, and we have hills here. It's somewhat similar, and there's water as well. And the populations are similar, about 800,000 or so. But except you can tell the water is slightly different colors, somewhat polluted there. But nevertheless, and I noticed some similarities. So what I want to discuss here, to begin with our excitement for the Higgs discovery. We all know that at the Large Hadron Collider, the largest scientific instrument so far, at the CERN, on the 1st of July, 2012, that was a milestone discovery. So this was the press conference, and these two people at that time was the leaders for the two experimental collaborations, and Joe Incandela, and he was the CMS spokesperson, and Professor Giannotti. Now she was the spokesperson for Atlas, and now she's currently is the general director for CERN. So they made an announcement that led to the next year's Nobel Prize. So the Nobel Prize citation rate for these two people's theoretical discovery for this the mass mechanism. Okay, so it explained the origin of all elementary particle masses, but it's connected to the discovery. It's confirmed because of this confirmation. So this the theory ideas got a Nobel Prize. They're confirmed by this discovery by the Atlas and CMS collaboration at the CERN, at the Large Hadron Collider, as I mentioned. So of course, this generated tremendous excitement for us. So we'll continue on these issues. So in short, the discovery was made to search for the two photons system, to search the so-called invariant mass. Mass in high-energy physics is, of course, in energy, as we know from the Einstein relation. The energy related to the frequency or wavelength. So thinking about the search for the invariant mass system is really thinking to search for some resonant signal, just like you detect from your radio or detect from your TV and so on and so forth, you get into this regime with a very short wavelength, very energetic system, and so on and so forth. So those small bumps turn out to be a significant observation. So at the early discovery, these were the early discovery with a 5.9 standard deviation from the flat distribution here. And here is from the other collaboration, CMS. And I think I should congratulate our colleagues in Brazil as well. And as far as I understand, that both CMS and others have a significant contribution from the Brazilian physicists as well. So they discovered this bump in this the spectrum here. As I mentioned, if you think about the search for the bump, it's a really search for the resonant signal. The resonant signal is at higher energies, refer to a shorter wavelength and a higher frequency. If you think about this conversion to our normal unit, so here the peak is around 125 GeV, 125 more energetic or more massive than the proton mass. Proton mass is roughly about 1 unit of GeV. But this 125, that corresponds to 10 to the minus 9 nanometers. So you see how far we have marched into the deeper and deeper level in nature. If you think about nanoscience, it's short. So this discovery here is made about 10 to minus 9 orders of magnitude, 9 orders of magnitude deeper to understand nature than the nanoscience. So that's they gave you the scale. Okay, so the discovery has been made, and also the detailed measurements further confirmed the discovery. And update to this year, summer this year, the peaks. Here is the Z boson. And here is the new discovery, the Higgs boson, around 125 GeV. GeV is units of pretty much close to the proton mass. The peak is so sharp, the measurements are so accurate, the mass determination for the Higgs boson is sub-percentage level already. It's tremendously impressive. After these a few years, the measurements, the mass determination has been in such accuracy, such accurate measurement already. Okay, so this milestone discovery is really leading us to a new territory, in the sense that this new particle discovered here is very different from any of the other previously discovered existing particles in our particle zoo, in our particle world. Okay, so it's not only made it to a scientific journal, attention from a science journal as well as social media. It's Time magazine. This Fabiola Gianotti was named as a number 6 or 5 run-up the most significant person for that year. So this is not easy. This, from the original discussion by the Peter Higgs and many other theorists, that was almost 50 years ago. I will discuss about this. And the experiments were carried out with all this preparation from the mid-90s. It's 25 years of preparation for all this machine and the detectors and the theoretical argument back and forth to make this observation. So this is a tremendously important discovery, but highly non-trivial to make it. So we should congratulate for science, not only for this, that this is really a tremendous success for science overall. Okay. So let's see what that really means. Come back to where we are for the current situation with the Higgs discovery. We know that nature is described by some fundamental interactions. All these phenomena come at different scales, different physical scales. But all the different scales hopefully will have some corresponding interpretation from the theoretical formulation and the forces, like the cosmological and the astronomical and the smaller and nanoscience and atomic and nuclear and so on and so forth. At the different scales, so far, we seem to categorize all these phenomena into, we call this 4 different forces. The one we learned earliest would be gravity. So the gravity turned out to be universal, no matter this, the planetary motion and also the apple falling onto our head. So that is we learned earliest for the simple gravity. Newton's gravitational universal law described the gravity most very accurately to a large extent. The other similar one has these electromagnetic properties, such as if you think about a static process, it's like a Coulomb's law. Both of these follow the very similar rules. Here is the force between 2 massive objects, and the 2 masses source. 2 masses of the source for the interaction. But it's inversely proportional to to the separation. Similarly, this is Coulomb's law. Coulomb's law is also proportional to product of two sources, the electric charge, and also inversely proportional to R squared. Inversely proportional to R squared is pure geometrical. It's because we have a three-dimensional space-time and spread out this flux. It goes like 4 pi R squared. It's purely geometrical. The dynamic, that's what we are trying to understand in deeper level. So these are the two gravitational and static electromagnetic interactions seem to behave very, very similarly. Okay. On the other hand, the nuclear forces, the weak force and strong force for the nuclear reactions are short-ranged. That's why we don't experience in our room here unless you go to a short-distance lab. So you can prove that. That is not only this 1 over R geometrical effect, but also has an exponential suppression. Okay. That exponential suppression depends on the range for the interaction. That range is parameterized by a quantity. It's, you can say the 1 over R0 or something. This R0 actually has a dimension of mass. So we'll come back to that later. So therefore, when we understand all these short-range forces, nuclear forces, and long-range forces, gravitational and electromagnetic, everything now fit into a very grand picture: quantum mechanical and quantum field theory, relativistic theory. So this line describes the whole world. Okay. So here you have this the electromagnetic field, and here is the gravitational field, and then the matter field around us, electrons and the protons and so on and so forth, and discuss about the Higgs. Those are the new field we just discovered to contribute to the mass generation. Okay, and then of course we integrate all possible paths, and this is the path integral, and they give you the quantum mechanical uncertainty principle and so forth. This single line in general describes our current understanding for everything already. Seems to be simple. However, as you will see that from my next many slides, I want to go over all these interactions piece by piece to see how we currently understand them, how deep we understand them, how much more we still ask for and to understand more. Let's go back to the electromagnetic first. So ever since you started the Maxwell equations, you know that the Maxwell equations can be parameterized from the E field. The B field can be parameterized according to the covariant formalism, like the field tensor. We call this F mu nu. The F mu nu will be given by this anti-symmetric field tensor, and this field, the tensor individually will give you the components for the E field and B field. That's what we measure, so on and so forth. And then this is called the covariant derivative. When you introduce the covariant derivative here, the whole theory possesses this particular feature that is the gauge transformation invariance. Remember that even in a Maxwell equation, if you perform gauge transformation for this A field to another derivative scalar field, the whole theory is invariant. So that means that there is a freedom that you can define your electromagnetic field, but without changing your observation, like E field and B field. So that we call that the unitary, one-parameter unitary rotational symmetry. We call the U1 gauge symmetry. Subscript means electromagnetic. So that one is compact. Okay. However, you see that if you incorporate this classical E and M to quantum mechanical theory, and you want to calculate these shorter and shorter distances, and consider the quantized form, you realize that the quantum mechanical description here can be described by so-called the QED, quantum electron dynamics, to a good accuracy. So of course, that's a Nobel Prize-winning piece of work by Richard Feynman and Tomonaga and Schwinger. Okay. So they calculated the quantum corrections to these classical properties. So this is the anomalous magnetic moment for the electron. So the theoretical calculation has been carried out many, many years to reach such a theoretical accuracy to the 10 to the 13th digit. And you compare with the experiments, they agree to 10 to the 13, basically 10 to the 12, 10 to the 13 digits. And this is tremendous success for the quantum mechanical system to describe electromagnetic interaction. We call the QED. This is really the most accurate theory in science. It's hard to believe any other theory could even surpass such a good accuracy. So the QED at these low energy measurements and the comparison is accurate theories. However, if you continue on demand the quantum mechanical description, to a deeper level, as I mentioned to you, if you have a probe, particle probe, to go deeper and deeper to probe this charge, because of the screening effect, this charge attracts some negative charges around it. So therefore, if you probe this to a deeper level, you probe a more and more true charge, and bigger. So that gives you the problem. That basically means that if you imagine if you probe this charge to infinitely short distance, it's almost infinity. So therefore, the charge here seems to change with your scale. And this is a generic feature, actually. This is a generic feature for quantum theory. So, okay. So we call this a fine structure constant. Atomic physics. Atomic physics over 4 pi is a fine structure constant. In the atomic physics, it's 1 over 137. So atomic physics, that's the fine structure constant. But it turned out it changed according to your energy scale. The deeper level you go, higher energy you go, the effective charge becomes diverges, so-called Landau pole. So this theory, the QED theory, seems to work so accurately around us, but it's not going to be a consistent theory forever. So that's the first lesson we want to bring up. Now let's look into the strong interaction. So therefore, we call this ultraviolet. This is invalid at arbitrarily high energy. So this is the so-called Landau pole. Keep this in mind. So let's really look to the strong dynamics. We call this quantum chromodynamics, the QCD. The quantum chromodynamics is to a large extent is similar to the electromagnetism, but except there are more interaction mediators. So there are more quantum numbers. We call this a color quantum number. It's ISO3, the unitary, special unitary symmetry. We call it color interaction. But each matter particle, like we call it quarks and so, has 3 different colors. In that case, the mediators, like the photons, in this version, will also carry some charges. Therefore, they have self-interactions. This formalism is similar to the QED I mentioned to you, matter field, and also the covariant derivative to keep the gauge invariance. This is, again, the Maxwell field, similar, but with additional index with this, the ISO3 quantum numbers. And in fact, there are 8 of them. 8 of them is a 3 squared minus 1. This is the group theory argument. Therefore, the interactions among those mediators, not only among the fermions, quarks, we call that, and among themselves, there is a anti-commutator relation. This is not 0. In QED, photon is not charged. Photon does not interact with the neutral particle at the leading order. But this one will interact with this because they carry charge themselves. Instead of being the screening effect, it is anti-screening effect. The gluons not only attract the negative charge, it also attracts its own charge because it's a charged particle. So therefore, if you probe this the gluon closer and closer, you find that the value is smaller and smaller. The true value is smaller and smaller because anti-screening. So it attracts more like charge. The further away, attract more and more. So if you go very far indefinitely, and the interaction becomes unbelievably strong. And that's why we don't see the colors. At some point, the colors all generate to something else. This anti-screening effect was calculated, and the evolution for this coupling constant, unlike this QED, it hits a Landau pole to become infinity. There's no, as long as the number of particles, we call this number of flavors of fermions, not too big. Of course, around 6 or so. So far, we have 6 quarks. As long as this is positive, it so turned out that this coupling constant becomes smaller and smaller logarithmically if you probe this smaller. This is called asymptotic freedom. So this asymptotically to a high energy, it is free theory. It's no interactions among themselves. This is tremendously important. This is tremendously important from observation aspect. First of all, it gives you prediction power. You can predict at the small interactions, you can do the perturbation theory, you know how to describe the weakly coupled system. And that is to give us the basis for us to be able to do higher energy physics, like LHC. like a future cloud. Otherwise, if the interaction becomes unbearably strong, we would lose our prediction power. But because of this property, we can do a higher energy experiments so that we can control the theoretical prediction and so on and so forth. Luckily, we have this property. Similarly, we seem to be able to understand the early universe Big Bang theory and comparison further and further. It's also thanks to this property. At the early universe, and the temperature is higher, and interaction is at higher energy, and all the interactions can be described by the standard model in the perturbation theory. So otherwise, we would not be able to. And this observation, of course, earned the Nobel Prize for David Gross and Frank Wilczek and David Politzer. Three of them obtained the Nobel Prize because of this observation to understand the strong dynamics. So that's interesting. Another interesting remark is that both of them were graduate students. It's rather rare for a graduate student piece of work to lead to such a profound impact and win the Nobel Prize. So in any case, so that is the theory, and this behavior has been verified by many experiments. This plot shows you that here, this is the coupling constant alpha as a function of the energy scales. Okay, you go to a higher energy scales, and you measure the coupling strength. So here, this is a 1 GeV. Actually, it comes from the tau lepton decay. So then the tau lepton decay to hydronic state. You measure these hydronic states. Then if you go to a higher energy, this is the CC bar bond state. And a little bit further, you have a 10 GeV-ish BB bar bond state. And to measure this, the coupling constant, indeed, the coupling constant becomes weaker and weaker. Then you go to higher energy machines, like E plus minus machines, many experiments, and we call the lab. And now later, we reach the Tevatron, Fermilab Tevatron, and now we even reach the LHC here in this region, a few hundred GeV, 500. You see that the changing with the coupling constant is tremendous. From 0.3-ish to 0.1, factor of 3 change. The coupling constant changes tremendously because of the strong interaction. The electromagnetic coupling also changes, but it goes other way, right? Bigger and bigger with a very small variation because the electromagnetic coupling is weaker. But this is tremendous confirmation for our theory. So that's at long distances, you see the interactions become stronger and stronger. Then the interaction becomes order for 1, the strong interaction becomes so strong, and they form bond state. When they form bond state, when the interaction becomes not strong, the bond state is a color singlet. Doesn't carry additional charge color anymore. That's you and me. So we form the color singlet, protons, neutrons, and pions, and so on and so forth around us, and that's why it seems to be short-ranged. It's about 10 to the minus 13 centimeters in that region. So that's around us. Around us, we only see the color neutral ones because interaction becomes so strong they form bond state. Protons, neutrons, and pions, so on and so forth. So that's the interpretation from the high energy fundamental theory to our observation around us. So that's the understanding with the strong interactions. Okay. Now we come to the weak interaction. Weak interaction is also very important. It leads us to the radiative decays. So this is beta decay. Beta decay leads you to a transition between a neutron to proton. It's charge current. The mediator here, the mediated interaction, carry a charge to transmit a neutral particle into a charged particle. And the other side must be charged as well, right? It's an electron and a missing particle, neutral particle, that's a neutrino. Pauli first postulated this neutrino. Interaction constructed by Fermi. Fermi basically mimic the electromagnetic currents, almost like one electromagnetic current to interact with another electromagnetic current mediated by electromagnetic force of photons. And he wrote down this interaction, one charged current on the other side, one charged current for the electron, the charged lepton side. But if you count the dimension, and this overall coupling constant is not like the electromagnetic fine structure constant or the QCD, it is dimensionful. Dimensionful quantity is extremely important. Once you have a dimension, you know there's a scale. Once you know the scale, you know something is going on there. It's a new physics. So therefore, if you simply estimate a number, this 10 to the minus 5 GeV squared, simply scale this, you know something around 100 GeV, there's a new scale. So in fact, that is 10 to the minus 18 meters or so in that region. So that is the weak interaction. It so turns out when you reach that energy, you can pop up the new physics, new particles, and that's the discovery of WZ bosons. So WZ boson, this is the W boson to be responsible for that. Now come to critical theoretical development. Steve Weinberg came up with this idea. He said, how to describe the theory of lepton? That is the seminal paper by Steve Weinberg, the model for leptons. And in fact, just last month, that was the 50 years anniversary for this paper. This paper appeared October 1967. So 1967, he first constructed the theoretical structure. And look at his idea. It's so profound. He said, well, leptons interact with some mediator, okay? But what could be more natural? To unify this mediator with photons. We know photon mediates electromagnetic, and these mediate the weak interaction. Would be nice to put them together into a multiplet. They belong to some similar property. They form a multiplet. However, there's a difference, as we mentioned. Photon is massless to mediate long-range forces, Coulomb force. But this mediator must have this mass dimension with this suppression I mentioned to you, exponential suppression. And so how to reconcile these two major differences? One is long-range massless, one is short-range weak interaction. So that's the major question. Okay. Of course, this is highly non-trivial for this question. Now let's see this the weak interaction theory then. The weak interaction theory was constructed by Glashow and Weinberg and Abdul Salam as well. So they postulate something similar to the electromagnetic, similar to the strong interaction, but with the necessary ingredients, charged state and so on, and a neutral state here. So they construct this very similar to gate theory, and similar to QCD, and also non-abelian, so more than one generator. But from the parity violation, we know that this interaction is a parity violated. The left-right asymmetric. In fact, 100% violated. It's completely left-handed interaction. That was from experimental observation, right? Parity observation in 1956, 57, 56, 57. That was an experiment. So they used this projection operator to pull out only the left-handed interactions. Okay. However, this gate interaction would prevent this the particle to be massive. Photon is massless. It has the exact the gate transformation invariance, but this one is massive. If you look at the mass term, this is the field plus the dimension-full quantity that is identified at the mass. If you perform the normal gate transformation, electromagnetic Maxwell equation will be invariant, but this is not. This term is not invariant anymore. That's why we are unable to write down the mass term if we insist gate symmetry. So that's the problem. In fact, the situation is even worse. The situation is even worse for the fermions, like electron. Electron is massive, we know. You know the electron has a mass, so if you bend it, it goes around. You can even measure the mass. TDD and Xing Yang first postulate the possible violation of left-right, and I think within a year, and it was verified from experimental observation then. So left-right differently under this interaction. Now let's look at the term. The mass term here, electron mass term, is the electron, and the dimension for coefficient. You found that. You can decompose these into a left-handed projection, right-handed projection, and therefore you can decompose this mass term into two pieces as a sum. But we know the left-handed one behaves different from right. This does not form a scalar number. It's almost like one is a 2 by 2, the two-component matrix. The other one is a number. They don't form a invariant number. So once again, if you believe this left-handed gate interaction, no particles can have a mass term. Not only gate bosons, all the fermions. So in this theory, it's complete massless theory. The theory seems to be elegant, but it doesn't reflect the reality. So of course, that's a problem. Now come to the important. Maybe the symmetry is not as rigid as you wish. So this comes to the concept of so-called spontaneous symmetry breaking. Now it becomes very common. This spontaneous symmetry breaking effect happens many places, even including the normal system like in condensed matter system and so on and so forth. What is the concept of that? The concept of this spontaneous symmetry breaking said your system, your theory formulation has this symmetry, such as gate symmetry. But your quantum state, the real world, quantum state is physics, and the Lagrangian is math. You may have a perfectly symmetric theory as a math description, but your physical state, we live here, is a particular state. That state may not respect the same symmetry. So that's the concept of spontaneous symmetry. Symmetry is broken, but by the particular state, by the life that we live with, rather than the formulas, rather than the math. So that is the situation. Right. Well, that must be a kind of a phase transition between the perfectly symmetric system and now to this system, and that happens very common. For example, like ferromagnetic systems. In the normal world, with the temperature, room temperature, other typical situations, and the domain wall, the domains in the magnetism is randomized. There's no particular orientation. Therefore, you can approximate the system by a three-dimensional rotational symmetry. Any direction, there's no particular orientation. However, if you lower the temperature below, and these domains may line up by some perturbation, and suddenly they line up together. That reach a lower energy state. That is presumably the ground state, quantum mechanical ground state. Quantum mechanical ground state is defined by vacuum. Vacuum is just the lowest ground state. So the new vacuum has particular orientation because of the domains. Therefore, the symmetry at the process before is spontaneously broken into a smaller symmetry. Instead of ISO3, it's ISO2. That's the example for spontaneous symmetry breaking. Theory is still Maxwell theory. Theory has no change. Theory originally and now is all described by the gate invariant to whatever the symmetric theory. However, your particular material, your particular system does not respect that same symmetry. There's nothing wrong, right? It's quite common. It could be very common. So therefore, the concept of spontaneous symmetry breaking is quite common, but very profound in connection with the system. Superconductivity and many fluid, many other examples all have these similar properties, can be described by similar properties. Okay, I'll come back to this point later. However, there is a showstopper. The showstopper is a pure mathematical theorem. The mathematical theorem proven by NAMBU and GOLDSTONE made some other additional observation. They claimed if this symmetry breaking is happening to a continuum symmetry, if the continuum symmetry is broken, just like we said there, and there's additional degree of freedom appear. So this is called NAMBU-GOLDSTONE boson. It's massless. It's no energy cost. Doesn't cost any energy to generate this additional propagating field. So this is the theorem saying that if there's a spontaneous symmetry breaking, and then it's necessarily lead to additional massless propagating field. That we haven't seen. Photons are the only massless electromagnetic field we know to carry on the long-range force, of course, except the gravitons. Gravitons are something that's weaker we don't discuss. But in nature, we haven't seen anything. But if this is true, it prevents us from implementing these spontaneous symmetry breaking ideas into our Lagrangian system. So that is a showstopper. So Pauli first criticized this so-called Yang-Mills theory. Professor Xin Yang was presenting his the weak interaction theory for SU2. Pauli asked, what is the mass? He said, well, I don't know the mass. There's no mass. And Pauli said, that's not the real world. The real world does not have this particle at all. And so therefore, Xin Yang could not even continue at the time. Okay? So, but the mathematics was there. But this is such a brilliant idea in such a convenient way, but we don't have the real phenomena to support that. It may be just a showstopper there. Now this is where the magic comes in. So this is so-called Higgs magnetism. And this is the magic coming in. So Peter Higgs and other physicists, I will show you all of them, they realized a particular connection between the spontaneous symmetry breaking and the continuous symmetry. So they claimed if this continuous symmetry is local to dependent on the space-time dependent symmetry, continuous space-time dependent symmetry, then this spontaneous symmetry breaking does lead to a GOLDSTONE boson, but this GOLDSTONE boson will be just one of the massless components to form a massive component. So that was the one together. So Peter Higgs proposed this idea in 1964, and about a month or so later, so there were another group. In fact, there was another group here, so I would them. So generate these almost 3 groups, and Engler brought actually in Brussels. In terms of time, the paper was published first in June 1964, and Peter Higgs' paper appeared in the physical letter B first, and it's about a month later, and finally a few months later, Keeble and this is the second paper from Higgs. This paper actually first time comment on the possible existence of the Higgs particle. So that was the first one, PRL paper at the very end. So it was a story about that too. And finally, a few months later, and Keeble and Hagen and Goronick here. This is, oh, by the way, Tom Keeble passed last year, and he was a brilliant physicist. And so Keeble and Goronick and Hagen here, and I think he's from Rochester, and he was from Brown University. And this is Engler. Of course, he shared Nobel Prize with Peter Higgs. And this is the Broad. He passed away. The reason for this picture is they were awarded with the American Physical Society Award. It's called a Sakurai Prize. So they received the Sakurai Prize a few years earlier, and this is the place that they received the Sakurai Prize in the US. But before the Sakurai Prize and the Nobel Prize, the Higgs discovery and Broad passed. But it's a very sad. But you see, that was almost the same time. There were quite a few people came up with the idea that the Higgs mechanism, we call the Higgs mechanism, was a collective work, and that tells you that the NAMBU-GOLDSTONE theorem is not necessarily a showstopper. Instead, in fact, it's really 2 magics to come together. One is that it generates a massless particle we never seen. The other one is that we want to have a massive particle, and it is not massive, but they merge together, form a massive particle that we want to have, just like the weak bosons, W and Z. Now, here is a full picture so far about the standard model. Okay, we have these matter fields. They have additional standard model construction. We call this the U1 hypercharged particles here, and we have this weak interaction, left-handed only doublets. Those are the singlets, and the 3 colors represent the color QCD, quantum chromodynamics. So that's all we have, and the particle contents are simply listed here. And then, in addition, we have this Higgs field in order to generate masses. Otherwise, these are all interactions are here, except all these particles must be massless in order to respect the symmetry. So therefore, even before the Higgs discovery, this model, from observation viewpoint, was confirmed over and over again to a good accuracy, and that was a standard model Nobel Prize shared by Sheldon Glashow and Abdul Salam and Steve Weinberg. So it was even before the Higgs discovery, before the confirmation for the physics for the Higgs potential. So you write down additional pieces to form this the Higgs potential. This phi here is the interaction. Let's call doublet. So this one developed a non-zero vacuum expectation value similar to what we said about the spontaneous symmetry breaking. In the symmetric phase, this is a perfect symmetric phase. If this is a positive quantity, you would have only quadratic and quartic form like this. However, if this coefficient here is a negative, in the beginning, it's the quartic term, the quadratic term dominance, and a very large field, the quartic term takes over. But in that case, the lowest point that represents the ground state, lowest energy state, is shifted. The lowest lowest potential energy point is ground state quantum mechanical vacuum. It's lower than the symmetric point. This is the spontaneous symmetry breaking, similar to the example I gave you from SO3 to SO2. So where this is a quantum state, vacuum state, this is where we live. We live here, shift away from the symmetric vacuum. And you produce the WZ and the particles and so on and so forth. You just generate some harmonic oscillator excitations here. We do high energy, you pop up a few particles here. We live here. So this is where we live. That is a quantum state that is spontaneously broken with respect to the original full symmetry. So that's about it. However, so all these particles will have a mass proportional to the coupling to this vacuum state. So the stronger coupling it is, so here is a vacuum background, uniform vacuum background all over places. And the different particles interact with the vacuum differently. The stronger the interaction is, the more massive this particle is. All the particle masses are simply proportional to this single parameter. All the elementary particle masses proportional to a single parameter, we call this vacuum expectation value V. So this is a so-called Yukawa coupling from the Higgs. And the bigger the Yukawa coupling is, the more massive this particle is. Look at the top quark, it's much, much heavier than the other lighter particles. And because the lighter particles interact with the vacuum with a weaker interaction constant. So that is the picture. Okay. So the gauge bosons have the same behavior, and the gauge bosons will also couple to the vacuum. The stronger the coupling is, the more massive this particle would be. Now, that seems to be a very consistent nice picture, but how do we verify this theory? Not only you want to only verify these mass parameters, but also you hope to see the additional degree of freedom of this particle. That's how you generate the excited state, just like a string. On string, the ground state has nothing, no vibration, but you hit it hard, you generate the excitation. So that what you do is you shake the vacuum hard. That's what LIC did. You shake the vacuum hard, you can probably generate the excited states. That's exactly what the LIC did. Huge energy to collide, and when they reach the frequency, high frequency, when they reach the wavelength 10 to minus 9 nanometers, this resonance came out. So that's what we want to verify this. Okay. Therefore, whenever you have the mass, there should be a Higgs, because the Higgs is associated with the vacuum. Therefore, whatever is more massive, that's more likely the Higgs will show up. So therefore, you need to go to a very, very high energy to create a very, very massive particle to begin with, and then shake off one Higgs. So that's basically why the discovery is so hard. You have to produce a very heavy particle to begin with, which naturally don't exist in nature. And you have to produce this first and then shake off the excitation. That's why. So any mass, it has a Higgs. So you can verify this by finding this one, of course. Now, so that's verified. So with Higgs discovery, now the standard model structure is completed. Mathematical structure is verified, so to that level. So it is so-called quantum mechanical. We do the quantum mechanical system. And it's renormalizable in the sense you can reabsorb the interactions with a scale dependence. And it's self-consistent. There's no Landau pole within the range. It's exponentially accurate to a high energy scale, maybe even all the way up to the Planck scale. The Planck scale is a scale where the gravity will come in with a similar strength with other particles. Say. So that may even be the case. Wonderful, maybe we're done. So somebody said most of the underlying principles have been formally established. And I don't know who this physicist is. A future truth of fundamental physics, physical science, are to be looked for in the just precision physics, to the 6 digits it goes on. That sounds wonderful, so we're done, the physics said. You think who said that? You know who this, the eminent physicist made this remark? Maybe some famous people now, just after the Higgs discovery? No, it was in 1894. Robert Michelson, who invented the Michelson-Morley, invented the interferometer to perform the Michelson-Morley experiment. Even by that time, he said, oh, we're done. We have a perfect theory to describe the whole world. That's what he thought. Unfortunately, it didn't follow a prediction, but fortunately, it led us to the deeper understanding for modern physics. His only experiment, Michelson-Morley experiment, showed inconsistency. Therefore, we moved further, and we understand the space-time more than Newton mechanics has led to the special theory of relativity. So therefore, this kind of statement may be encouraging, but it's just a too brief extrapolation. So therefore, I don't think it would be a guide for us to probe the nature into a deeper level. Okay. So history may repeat itself. Now we have a very good theory, consistent framework, and it's just inconceivable that theory would describe 15 or 16 orders of magnitude above the theory to the Planck scale. So therefore, from now on, I want to argue why we don't believe this statement, why we are searching for deeper answers to certain questions. Okay, so that's what we want to say. Under the Higgs Lamppost, what do we know least? The Higgs particle was just discovered, and the Higgs particle is the we know least. Anything associated with the Higgs should be studied carefully and to possible level so that we can learn some hints to a deeper level. This paper, the two papers, one from Atlas, one from CMS, I showed you from one of the first slides. Each paper has received almost 8,000 citations. You see how profound the impact is. And the citations not only by us, not only by particle physicists. It has interpretations and extrapolations in particle physics, in the standard model, beyond standard model, and possible application in astronomy. And the cosmology, particularly the scalar particle is discovered. Scalar particle, if you have scalar particle in your theory, you don't have to be apologetic anymore. Previously, we have never seen a scalar particle. Any theorist to introduce a scalar particle, well, by the way, I'm very, very sorry, I have to do this. Now you don't need to apologize. A scalar particle exists in nature. Make use of that to do whatever to explain your theory. So implication in the cosmology, string theory, and so on and so forth. And I didn't read this part carefully, even philosophical implications a lot. I never read this carefully, but so you see the implications. Now let's make a few observations about the Higgs sector to see what we have, in fact, what we have learned we haven't talked about. So first of all, Higgs mechanism does not mean the existence of a Higgs particle. The Higgs mechanism only tells you to have these Goldstone bosons to merge into another the gauge bosons to form mass. That's it. However, the consistent theory has additional piece. That is Higgs boson. I would not go to details, but this is a mathematical formulation. So this is so-called a nonlinear sigma model. You do this symmetry, this theory perfectly, this gauge symmetry. But it parameterized in such a way there is no Higgs boson. But this theory is not going to be valid to an arbitrarily high scale because of the probability conservation and all this very, very simple quantum mechanics argument. This theory would be valid up to 2 TeV. But obviously, this theory is not correct because we do find additional degree of freedom at the Higgs boson. So therefore, the existence of this Higgs boson teaches us a lesson already. Teach us a lesson that the renormalizable kind of argument to have additional symmetry may be the correct way. Maybe the fundamentally important guidance for us to form any theory. So the Higgs discovery teaches us a lesson already, even on the surface. So the Higgs mechanism, only the mechanism did not mean the existence of particle, but the existence of the particle teaches you a deeper fundamental principle already. Now, so I mentioned the Higgs potential has this form. When we have two measurements, one is the weak interaction. We said the weak interaction W mass, and now we have the Higgs mass. These two measurements fix these two parameters already. So this parameter lambda is determined by this the vacuum expectation value and the Higgs mass. It's about a 0.13-ish. This is a dimensionless coupling. Dimensionless coupling, normally in our general concept argument, is a new force. You may view this as a discovery of a new additional interaction beyond the four forces. But how we understand this is not that clear yet. We have to go further and do more to understand what is happening for this additional new interaction, new forces. Okay? Maybe it is induced by some other sector or interactions. Maybe so, like for example, Landau-Ginzburg. Ginzburg theory described this the second order phase second order phase transition for superconductivity very, very well, but it's not fundamental theory. It's only parameterization. Okay, I will come back to this more. Van der Waals force, the atomic molecular force. It describes the features very well. I think it's 1/r to the 6th power or so, but it's just collective. Coulomb force is fundamental between the two fundamental charges. maybe this force has something to do with more fundamental theory and give you this quantity. We need to go further to understand that. So this is possibly a new force, but new force may not be the end of the story. Okay, so that's another thing we want to say. Of course, there are theories to explain this. For example, you introduce additional symmetry to make connections. Supersymmetry is the most prominent example. Supersymmetry introduces symmetry between the fermions, spin half, and bosons, spin 0 and 1. So because of symmetry, this coupling constant is related to the other interactions. Therefore, you can predict. This coupling can be predicted. This coupling lambda would be equal to, at the leading order, is equal to the left-handed coupling squared, and the hypercharge squared divided by 8, in theory. It's a little bit too small to account for this observation. So therefore, supersymmetry is not working yet. We haven't seen supersymmetry. But it gives you a very deep insight. Maybe additional symmetry is at work at somewhere to give you the interpretation for the Higgs sector. Other strong dynamics, like a strongly interacting system, such as we said that the low energy QCD and so on and so forth. You could also generate this new interaction here. But on the other hand, you generate a little too big. So either new theories from the weakly coupled supersymmetry or strongly coupled hadronic dynamic, strongly interacting sector, none of these seem to fit the current observation yet. But it's quite inspiring, right? It inspires us to think, to ask further questions. That is the second observation. Okay, so we can say that the supersymmetry does not seem to work yet. It's a little bit too light for Higgs to be heavy, and the strong dynamics is really too heavy to the Higgs to be light. So none of these seem to work yet. But we need to go further. Okay, so at the higher energies, if you make this lambda similar to ask the same question, we said the electromagnetic interaction becomes stronger and stronger. QCD becomes weaker and weaker. How about this lambda? You can even ask this question too. Let's see symptotic behavior. It so turned out that this one has a Landau pole because of the symmetry. And this particle here, this coupling constant becomes bigger and bigger, eventually blow up at some very, very high scales. So this is the overall situation. With this 126 G, 125 GeV in this region, this is the Higgs mass parameter. And here is the consistent range. So the 126 GeV parameter will more or less in the consistent range. This is interaction is too strong and not give you the correct description. And this is interaction is too weak that the top quark drives our vacuum into unstable universe very soon. Okay, so it's a vacuum instability. So therefore, if the Higgs mass is somewhere here, it's really in the region that we really need to understand more about the standard model structure in order to see the high energy consistency and high energy behavior. So therefore, this coupling constant here is very important to study. So for the standard model to be consistent to the Planck scale, we probably hope to have some new physics somewhere in between to help and to get the Higgs coupling constant here within the acceptable. I'm saying that if the Higgs mass is too light, the top quark is a little bit heavier, then our vacuum, the early universe vacuum now may not be stable. It's maybe quasi-stable at some time the vacuum may even disappear. So it's another observation that we should watch out. Okay. So the third observation is that the electroweak phase transition for the Higgs mechanism is very much parallel to the superconductivity. It is a superconductivity, actually. Let's make this connection. I think it's fundamentally important, but observationally not quite yet, but fundamentally important. Let's just see this situation. Now, so this is a superconducting material in the normal temperature. We know in the normal temperature, it propagates into the material, and with its massive photon propagation, the speed changes a little bit due to the index of reflection. But nevertheless, this is the energy momentum relation. We call this the dispersion relation, similar to this photon propagation. Okay, so that's a normal case. However, you cool it down. You cool it down to change the temperature to lower than the critical temperature. Then this material undergoes superconducting phase transition. In that superconducting phase transition, suddenly there's a Meissner effect. The Meissner effect expels the electromagnetic field. Electromagnetic field cannot propagate inside the superconducting material in long range. It does propagate a little bit. It's called a London penetration length. It's exponentially suppressed. The electromagnetic field propagates a little bit and disappears. So that is the length to propagate that is called a London penetration length. It's the length is described by the parameter lambda, and lambda is inversely proportional to some mass dimension. Okay, so that is the situation. In fact, superconducting process, superconducting phase transition leads the electromagnetic field inside there as massive particle. Photons acquire a mass due to this process. The photon mass is, let's say, estimate conventionally, empirically, is about 1 part of 1,000 of the electron mass. So the superconducting phase transition happens to be at a very low temperature, a few Kelvin. Typically, BCI theory, we understand that's a typical situation. Now let's see electroweak correspondence. Electroweak correspondence corresponds to the W mass. The W mass translates this into a 10 to the 15 Kelvin. Okay, then this is W mass. The massive gauge boson mass here, this is the corresponding temperature. That basically tells you after the Big Bang, when the universe cools down to as a cold at 10 to the 15 Kelvin, and that's too cold universe, and we underwent electroweak phase transition. So that's the real phenomenon. We are living simply in an electroweak superconducting environment. That's it. So why the W and Z are so massive, only conduct a very short-range interaction? That's because of this. Photons would be a short-range interaction as well. Okay, so it's exactly the same parallel phenomenon, but at a different energy scales. It's much earlier phase transition, much heavier energy scale. How to do the application? I haven't figured out any possible observation for the electroweak in our current laboratory yet, because energy scale is much too high. The LIC is only barely reaching the Higgs field. Okay, so let's see. Let me be rather quick here. So I had a comparison between the Landau-Ginzburg theory and our electron. And it's a Landau-Ginzburg theory. It's only a parameterization for this situation. However, we in the electroweak sector, the Higgs is an elementary particle, and the Higgs actually is very weakly coupled, very narrow, and it's different from the Landau-Ginzburg. In fact, it's very interesting to notice that there was a measurement. Where is it? This one. In fact, in 2014, inspired by the Higgs discovery, our condensed matter friends went on the trouble to shake the material harder and harder. Finally, they discovered some resonance. They discovered the Higgs equivalent. But of course, in that case, it's a composite system, collective system. It's not the one that we have our Higgs very sharp, narrow resonance. But in that situation, there are possible corresponding phenomena as well. Okay, so this actually was the first one. It's very much inspired by the Higgs discovery, and you carry on the experiment. So this was there was a collective mode, it's a pseudo-spin collective mode, to lead you a resonant signal very similar to the Higgs phenomenon. You could even call that a Higgs particle, but it's different from what we are discussing. What we are discussing, the fundamental Higgs particle. Okay, now let me ask a few questions that we really want to get an answer, so that will lead you to think about the future experiments. So since time is running short, let me be rather quick. First of all, we measure the Higgs mass at one parameter. We measure the second parameter from the vacuum expectation value. We fix the quadratic of potential. But we don't know where the quadratic potential is the whole story. We don't know, maybe the potential is not as simple as one. Maybe the potential is like this. Maybe potential actually is somewhat more complex than that. So we need to measure the additional interactions, additional terms in the interaction, so that we can see what is happening during the electroweak phase transition. That has a tremendous important consequence. If you have something new beyond the electroweak scale, then the first two leading terms may not be the full story. You may have additional higher dimensional contributions terms we call the dimension 6 operator. Maybe you even have a non-analytical functions to describe the potential rather than simple quadratic terms. Any of these would modify the theory. The third term, we call it the triple Higgs coupling. The 3 Higgs coupling is the first non-zero term to appear beyond the current 2 measurements. If you measure this, the additional term, it may modify this significantly. If this is modified by order 1 deviation, our electroweak phase transition may be dramatically different from Landau-Ginzburg. May give you the strong first order phase transition. If we have a strong first order phase transition, many things could happen, such as baryon number, asymmetry, and so on and so forth. We did not get a chance to talk about that. So therefore, the first question to me is that we want to know the Higgs potential to a better accuracy. So I'm not going to tell you the supersymmetry is our goal to search. I'm not going to argue that the strong dynamics is more likely. I only want to honestly ask the questions. Given the Higgs discovery, what do we want to learn? What do we want to know? That's absolutely the correct way to think about the scientific development and to think about how to make progress. Rather than saying that the supersymmetry is not discovered, therefore it's failure. That's not the way we do science. We do science, ask fundamental questions and answer the fundamental questions. That's what we do. This is the first question we want to know. We want to know the Higgs potential to a better accuracy. So that's the first question. Second question is about so-called naturalness. So the Higgs scalar here does not have additional symmetry to protect you. When you take into the quantum mechanical effect, the quantum fluctuation generate a huge correction to the Higgs potential. Okay? So then instead of multiplicable correction, is additive. You want to modify these quantum corrections to the observable 125 GeV. You need some other new state to come in not too far away from it. If this is too far away from it, then you have to tune these parameters in such an unpleasant way to give you rather light 125 GeV. Okay? If you assume this is valid all the way up to Planck scale, as I gave you the possibility set, you need to cancel the first 33 digits. The first 33 digits will have to be precisely cancelled by the parameters here so that you are left with the observable 125 GeV, because you push this all the way up to 10 to the 19 GeV already. So that's just conceptually unacceptable. It's not mathematically wrong. Mathematically, of course, you can do fine-tune, but it just it doesn't taste right. We don't think this is the case. There's nothing somewhere in between. Somewhere between must have some new physics, new reason for that. Okay. So this is 10 to the 33. If these numbers don't impress you, okay, let me give you another example. This is my daughter. Show my daughter, right? So one time she was asking me, "Hey, Dad." So what happened? Oh, I saw that she was playing with this can, and it's standing there. I took a picture, and it fell. Even give me 2 seconds or so to take a picture. Why she was surprised? Because it's fine-tuned. She was so. You must have. So she thought it was unbelievable. But that fine-tune is not a big deal. So if this centimeter, the supporting area, and millimeter supporting area, centimeter the can area, it's only -10 to -3 fine-tune, which means that you try 1,000 times, so you may have a chance to make it happen to be there a little bit, even unstable. Okay. So therefore, this 10 to -3 fine-tune, people would accept. If you walk in to see this happen, you would be like her. Something happened. What must be fundamental superstring theory, something to give you this, right? So you would not accept this as a natural. So that's why you think about the 10 to the 33 cancellation. We really don't think that's the final story. We just don't think the standard model should be final story. That's my second question. Third question is about of course, naturalness. You do need new physics. I will skip the details. You do need possible new physics to help you in between, way before the Planck scale, and to help you. We call the supersymmetry the one solution. Composite strong dynamics, another solution. That's the 2 typical representations. It's not a full story, but it's a representation. I will skip this. And you search for these particles and so on. Third question, dark matter. We know it's from observational aspect. We seem to have a very strong evidence for dark matter discovery. I think it's fair to claim dark matter has been discovered, but only from gravitational interaction, gravitational aspect. We think the dark matter may have a lot to do with the particle physics. That's something we haven't discovered. We have no clue the dark matter, the mass, no clue about dark matter, the interaction strength. But dark matter sector may couple to this the Higgs in this way. The Higgs, if you form this, we call it form a singlet. This singlet does not talk to standard model particle anymore. Therefore, it can talk to any other particles. Any other particle may not talk to our standard model directly. This is we call it portal. The Higgs may be the messenger in between. So I think the search for the dark matter, searching for the Higgs property may lead to some fruitful direction for dark matter. So basically, because of time, I only pose these 3 questions. These 3 questions, I think, is very pressing, and all not only based on the theoretical construction, but also based on the observation, and we want to move forward to answer those questions. Whether it's some fundamental theory will tell us, supersymmetry or something, that's not our goal. Our goal is to understand nature to a deeper level and understand these questions and seek for solutions for these questions. So basically motivate and explain the Higgs factor and lay out the unsatisfactory questions and problems for you. And I will just quickly go through this. This flavor is another problem that everything is proportional to V, but the drastic different masses. It's also unsatisfactory. Lay out these future things. Okay, so let's skip this theoretical argument. Now we have this fantastic machine. So this is our workshop. We want to discuss the existence of the search and the possible future and interpretation. So, and this machine is operating well and even surpass the expectation, surpass the designed parameters. We accumulate this much, our Atlas CMS colleague accumulate this much data, and 10 times more coming, in fact, almost 100 times more for this called run 3 and run 4, and so on and so forth. So this LIC is going to lead. LIC is going to lead us for the next almost 20 years. So we're going to continue to work on it. Hopefully, we answer some of the questions continuously. But that's not all I want to say. I want to tell you something more. So this was an article appeared in Nature in 2014. So it laid out the possible future options. This little circle is the existing machine is LHC, 27 kilometers. So that's the existing LHC. All these dashed circles are the virtual machines that could be the future machine. Okay? So there are 2 regions to think about this future seriously. One is a CERN. We want to estimate what may be taking us to go to the next stage. And another one is in China. These 2 places are trying to contemplating on the possible upgrade beyond the LHC. Beyond, it's basically around the time 2035 or after. So before 2035, roughly we will have the LHC to lead the field. So we hope to do as much as possible. But these are few rings here. I will quickly go over them. So this is the 2013 American Physical Society study. List the parameters if you are interested in details. So this is reference you can look into. That is not what I want to do. But before that, there's a mature design. We call the linear collider. It's called an international linear collider. And so far, the proposal was proposed in Japan. So this is under the very serious final stage of a review. Hopefully, within a year or so, we will know the evaluation, the conclusion from the Japanese government. So the Japanese government would give us an inclusion whether to recommend the construction or not. This is the site in northeast region of Japan. And the site was chosen already, and the design was very mature in terms of the physics argument, in terms of the technology, the technical design aspect. It's mature, but it's for the moment, it's still under serious review. So we call this initial Higgs factory. So you can run this near the Higgs and the Z boson there. You can study the Higgs to great detail. So I will give you some numbers quick if I can. So this is a CERN version. Here, this ring for the existing LHC is 27 kilometers. But the future consideration is about 100 kilometers or so. So that the energy will be increased by almost 1 order of magnitude. In fact, by a factor of 7. Factor of 7 to theory is 1 order of magnitude. Okay. So you increase this, the energy by 1 order of magnitude from LHC to this 100 TeV. And that takes us to a much deeper level, shorter distance, and hopefully to help us answer those few questions I raised. So that's the current situation. And a similar concept was discussed in China. It's still under serious discussion. And so they hope to choose a site on the northeast part of the country. And here it's about 300 kilometers east of Beijing. Beijing there, kilometers away from Beijing, directly there. And geography, geology, all these studies went through seem to be okay. But with no funding, no final decision, no final design yet. There's only concept. So physics, with theorists start thinking about the physics already, like us. So we think about the physics output and so on and so forth. So because of time, really quick. So here is the International Linear Collider to produce the Higgs. This curve tells you the cross-section, basically the production rate. So here is a 200 universal fundamental bond production rate, the Higgs near the threshold. If you accumulate enough luminosity, the target is 1 million Higgs. The target, so you call this a 5 universal aquabond luminosity, which is not unreachable. But the target is to, at this Higgs factory to produce 1 million Higgs to study the Higgs detailed properties. So that's all the E plus minus machine. So I would be quick. So if you increase the LHC energy from 14 TeV by a factor of 7 to 100 TeV, you increase the production for new physics processes, such as the Higgs pair production is increased by a factor of 40. You can do a lot better at that machine. The top quark supersymmetry partners and so on forth, it can be increased by the production rate by 1,000 times more. So therefore, this has a tremendous changes. And you can measure many detailed properties and so on and so forth. So because of time, let me skip the detailed situations. Now I'll give you 3 answers to my 3 questions. Is how about the naturalness? If the Higgs is natural, and whether there's new physics around it, you can search for new physics. You don't find a new physics, you push this naturalness problem even sharper. So if you don't find Higgs at the LHC reach the 1 TeV region, then you push the fine tune to be worse than 1%. However, if you go to the future collider, you improve this by another factor of 10. You push this fine tune to 10 to minus 4. Remember, 10 to minus 3 is quite unacceptable already. Normally in our daily life, 1% fine tune happens. So like a sun and the moon size just happen to be like about a percentage of fine tune. Of course, it's a different argument. But nevertheless, if you fine tune 10 to minus 4, we think we have formulated our naturalness argument to a harder and deeper level. So that's the future collider. And about the dark matter search, in connection with particle physics. But here is a common plot for the dark direct search. So this is a dark matter direct search exclusion. If the dark matter cross-section has been included to many order of magnitude below the electroweak interactions. Here, the horizontal is the dark matter mass to be probed. On the low mass region, this region has very low sensitivity from direct search. The reason is if the dark matter is very light, it doesn't kick the detector very much. So it's very insensitive to probe this. So that is in this case. However, very light dark matter is fantastic for us to search at the LHC because they carry a huge kinetic energy, missing kinetic energy. That's what we call the missing energy to search for. And this is a really good place for our collider to complement the direct search. The other mass extreme, in the very heavy mass region, the direct search rate, underground lab direct search rate is getting lower and lower. This is, again, very difficult to be sensitive. Again, it's very good for us. We have a huge energy threshold. We have a 100 TeV machine. This, a few hundred GeV will be opened up. So therefore, the collider search will tremendously complement the direct dark matter search for both most difficult regions. So therefore, the future collider is strongly motivated, even for the dark matter search. Finally, so this is the coverage. I will skip the coverage. We have numerical calculations to show the coverage. finally, the new particle, if you have a new W and Z new particles, you can probe this very, very far away. The bottom line is that you can extend the LIC search by factor 6 to factor 8. Okay, so that's the extension that the new machine can be. I think that's pretty much all that I can motivate the collider and tell you the results. Let's see where we are. Okay, now we have discovered the Higgs particle in the electroweak sector. We want to understand more about the phase transition process. These two parameters give us a very boring second-order phase transition, very much like a Landau-Ginzburg parameterization. We don't know that's true. We want to understand the third term. If the third term turns out to be small, the first two terms are good approximation. You live with that. But if the third term is big, next machine is a machine to solve for that. Now we have the dark matter puzzle. And dark matter composed almost like 20% or more than 20% of the universe budget. We don't know what that is in terms of the properties. They exist from the gravitational measurements, many different observations to lead to that. So dark matter search will be complemented from the collider search. That's what I mentioned to you already. So therefore, we're pushing to the one level deeper and to understand the fine-tune. So therefore, the Higgs indeed is a lamppost we want to work around. We want to study Higgs in connection with the next level deep understanding. I think this basically my basic knowledge, basic message. Basic message tells you that the Higgs discovery is a new class. So in summary, the Higgs boson is a new class. The Higgs boson has a connection with the energy frontier to lead to our future matter, and direct connection with the possible mass generation, including neutrino mass that I did not discuss, and possible cosmic connection with the dark matter and so on and so forth. Studying the Higgs should be fruitful for us to understand nature to a deeper level. Naturalness argument, I call it. Naturally speaking, Higgs should not be alone. Higgs particles should have siblings and come together to solve these problems. And the future collider will lead us to good measurements. LIC is going to lead the way for the next almost 20 years. It's only be able to reach the accuracy for the coupling constant 10%, and 50% even controversial, whether you can reach the 50% accuracy for the triple Higgs coupling. And if the Higgs coupled to dark matter to carry away missing particles, and accuracy is 20% roughly at best. But a future Higgs factory, and we'll call it a super proton-proton collider, it's 100 TeV1, will improve all these measurements. 10% measurement, these will be conclusive to declare whether the standard model is basically right. Therefore, the electroweak phase transition is just a boring second order or actually different. So therefore, there are many important questions to address. So that take us future collider consideration and the possible design. The coverage for the future collider will extend the coverage for the LIC and tune to a much more difficult situation or discovery, and the particle dark matter to multi-TeV. So I think it's a lot of excitement to come in the near future. So students here, please join us. Thank you. Sorry, running over time.
Well, maybe let me ask a question from